Welcome back. In this video, we'll talk about the second derivative test. So this is another way that we can classify critical points. That is, points for a function where the derivative either equals 0 or doesn't exist. So the second derivative test tells us if we've got c a critical point, we should look at the second derivative of f and evaluate it at the point c. And the sign of the second derivative tells us what to do. So in the first case, if the second derivative evaluated at c is a positive number, well then our critical point there is a local minimum. And you could probably guess that based on the shape. Remember, if the second derivative is positive, our function is concave up. And if we've got a concave up or bowl shape, then the place in the middle where the tangent line is horizontal is a local minimum. On the other hand, if the second derivative evaluated at c, our critical point, is negative, well then it's concave down, and that gives us a local maximum at the critical point. And the last and unfortunate case is if the second derivative is equal to 0 at our critical point, then the test fails. That is, it tells us absolutely nothing. It could be a local max, it could be a local min, it could be a saddle point, or something else funky could be going on. There's really nothing more we can say without trying something different. So something different could be trying the first derivative test, or just looking at the graph or plugging in points, but we can't say for sure. So let's try this out. Let's use the second derivative test to classify the critical points of this function, x over x squared plus 1. So I'll use the quotient rule to write down the derivative of g. And now the denominator will never be 0, but if I factor the numerator, I'll see that this function g prime has zeros when x is minus 1 or 1. That is, these are two critical points for g, the only critical points for g. And to find the second derivative, well, I won't use the factored version because we would need to use the product rule to take the derivative of that. But this other one, 1 minus x squared over x squared plus 1 whole quantity squared, I'll use the quotient rule here. I'll carefully take the derivatives, I'll factor and cancel and factor, and we see that the second derivative of g is 2x times x squared minus 3 all over x squared plus 1 cubed. Now, to apply the second derivative test, I could just plug in here our critical points 1 and minus 1. I would find that g double prime of 1 is minus a half. I would find that g double prime of minus 1 is positive a half. And the second derivative test tells us what to do there. I'm going to make it a little more complicated because we're going to use what's coming a little later on. So let's do something like we did before. We'll make a second derivative chart for this function g. So just like we do with the first derivative, a second derivative chart will show us where the second derivative for g is positive or negative. It's helpful to know when the second derivative is 0, that is where it could switch from positive to negative. And the way we factored it, well, you can see that this happens when either g is, when x is 0 or when x is plus or minus root 3. So we can check by plugging in points or multiplying and thinking about the signs that the sign of g double prime switches from negative to negative to positive as we move from less than minus root 3 up to between minus root 3 and 0, and so on. Our critical points minus 1 and 1 live on this number line too, so we can just read off of the second derivative chart the signs there we find that there's a local minimum at x is -1 because the second derivative is positive, a local max at x equals 1 because the second derivative is negative. So the reason I wanted to do the second derivative chart was so we can talk a little bit about inflection points. So maybe you remember, or maybe you're just seeing it now, an inflection point of a function is a place where the concavity changes. That is where the second derivative switches sign from positive to negative or from negative to positive. So to talk about the inflection points of this function g that we just looked at, well, we've already done all the work. We saw that the concavity changes, the second derivative changes sign 3 times, that is at -√3, at 0, and at positive √3. And now putting together all this information about the concavity and the maxes and mins, we can actually do a pretty good sketch of what the function g might look like. Now the scale is almost certainly off here, but in terms of the concavity where it's shaped like a bowl or shaped like a cup, where we've got our max or our min, those are right. And so then the last thing I want to show you is a little bit different. Consider this sort of hourglass-shaped vase. And I want to imagine how this would look if we started filling it up with water. So not with respect to time, but as we added, say, a constant amount of volume, how the height would change. And if you think about this for a little bit, I think you can convince yourself that to get, say, that first centimeter of water on the bottom, we might have to add a good amount of water to the vase. But then that next centimeter wouldn't take quite as much water. That is, the same amount of volume would take us a little bit further up the vase. So we can start graphing this. And as we get closer to that slender part in the middle, the same amount of volume will take us up further. So the rate at which the water height is increasing is actually going up. Until we get to that most tapered part and this trend reverses. Then we have to start adding more volume to see the same amount of height increase in the water level. So this height versus volume graph might look something like this. And the point where our graph changes concavity, the inflection point right in the middle, corresponds to that most tapered part in this vase. So we can see sort of a physical situation of how an inflection point might happen. So I'll leave you with a challenge. Maybe think about what a vase would have to look like if its height versus volume graph would look like this instead. And actually try one more. Try this one in purple too. So this was the second derivative test. We'll see some more examples in class, or you can try some in the book.